Good afternoon, everyone. Welcome back to the COP26 Cryosphere Pavilion. My name is Heidi Silvestre. I'm the Director of Outreach at ICCI, International Cryosphere Climate Initiative. And it is my pleasure to open the second round of presentations given by our early career scientists who are volunteering here at the pavilion. And my great joy to introduce Helen Millman from the University of New South Wales in Australia. Helen, the floor is yours.
Thank you very much, Heidi. So hello, everyone. Today I'm going to tell you all about my adventures in Antarctic ice sheet modelling. So part of the remit for this talk was to tell you a little bit about myself and how and why I became a glaciologist. So that is what I'm going to talk about in the first part of my presentation. And then I'll tell you a little bit about my research. So I come from South Devon in the southwest of England. As you can see, I've put a handy map up there for you. And this is a photo of me and my dad that was taken a few years ago. My dad was a bus driver and he was dyslexic, but dyslexia didn't exist when he was at school. So he was hit with a ruler and told that he was stupid and would never amount to anything. He left school at 15, barely able to write, and his only qualification was a 25-yard swimming certificate. But he worked really hard to build up the family business, and which is coaches, which is why I have a photo of us, and so that he could give me all the opportunities that he didn't have. And he spent a lot of his hard-earned money on my education because he wanted me to be able to go and do whatever I wanted with my life. And what did I want to do with my life? Well, I wanted to go and study glaciers. And why did I want to study glaciers? When I was around 11 or 12, I saw the BBC documentary Pole to Pole with Michael Palin, and I saw Michael Palin sitting on the toilet in Antarctica, and I thought that was the most fantastic adventure I could ever imagine. Here he is sitting on the toilet in Antarctica, this photo. And so I started to dream that one day I too would be able to sit on the toilet in Antarctica. I ended up doing a degree in geography, followed by a master's in glaciology at Aberystwyth University, where all the best people study. And then I started a PhD. And I found myself in Antarctica. By chance, I ended up in the Patriot Hills, which was exactly the same part of Antarctica that Michael Palin went to. Unfortunately, I don't have a photo of myself sitting on the toilet, but I do have this photo of the bucket they gave me to pee in. From Antarctica, I went straight to Sydney, where I spent 3 years at the Climate Change Research Centre at UNSW, sitting in a windowless office, learning how to be an ice sheet modeller. Which brings me on to the second part of my talk, which is a quick introduction to ice sheet modelling. So what makes an ice sheet model? First, we look at the physical process. Then we devise equations that describe that physical process. Model developers then turn those equations into computer code, and then someone like me comes along and uses that ice sheet model to help us to answer questions in our research. I'm going to tell you a little bit about some of the mathematical descriptions that make up ice sheet models. The first of these equations is Glen's flow law, and this describes how ice crystals respond to stress. How ice deforms is really dependent on temperature and stress. This graph shows how the ice flow changes as stress and strain increases until we get up to the top, where the stress and strain becomes too much and the ice fractures, and that's where we get a crevasse. You've probably been wondering what this is in the top right-hand corner. It is an artist's impression of an aircraft carrier made of ice. And during the Second World War, they tried to build this. Lord Mountbatten was the chief of combined operations, which was the department that invented the D-Day landing craft and the Mulberry Harbour. And he employed a man called Geoffrey Pike, who came up with things that might just win the war. And one of the things he came up with was some stuff called picrite, which was ice mixed with sawdust, which made the ice really strong and it didn't melt quite so fast. And Lord Mountbatten was really impressed with this, and he took a lump of it to Churchill. And when he arrived at number 10, he said he was told the PM is in the bath, and he said that's exactly where I want him to be. So he walked into Churchill's bathroom and threw the lump of this pykrete into the bath, and Churchill was really impressed with it. So they tried to build an aircraft carrier out of it in Canada. And it was a disaster because even with sawdust in it, the ice still flowed and it melted. But the point of all this is that because of Geoffrey Pike, the physical properties of ice became a matter of national importance. Spitalfields Meat Market was turned into an ice lab, and lots of students from Cambridge were brought in to study ice. And one of those students was John Glenn, and his work led to this flow law that forms the cornerstone of today's ice sheet models. Another cornerstone of ice sheet models is the Stokes equations. These describe the way a fluid responds to stress. Although ice is solid, it flows like a viscous fluid, and these equations give us 3D velocity and pressure fields. This is the algebraic jungle, and it takes a lot of computational power to solve the full Stokes equations. So model developers often only use the parts of Stokes equations that we really need. And these are the approximations of Stokes' law. We have the shallow ice approximation, which describes how grounded ice sheet flows. This is shown in the blue lines. And the shallow shelf approximation, which describes how ice shelves flow, which is shown here in the red lines. And both of these approximations together describe how ice streams flow. The ice sheet model that I use is called the parallel ice sheet model, and it is a hybrid model because it has both the shallow shelf and shallow ice approximations. This is some of the code. This is what my model looks like pretty much to me. And it's designed to be easily coupled to climate models, which is good because that's what I use it for in my experiments. And this is the data that I fed into the ice sheet model. Geothermal heat flux and basal topography came from measured data sets, but the air temperature, precipitation and ocean temperature and salinity data that I used came from climate model outputs. And in the last part of my talk, I'm going to tell you about my PhD research, which was all about Antarctica's contribution to sea level rise during the last interglacial. As this image shows, Antarctica is very large. It holds 90% of the world's ice, which would raise sea levels by 60 meters if it all melted. Antarctica can be split into 3 distinct areas: East Antarctica, which covers the largest area, has the thickest ice and the coldest temperatures on Earth; West Antarctica, over there, which has the lowest bed elevation and slippery marine sediments at its base; and the Antarctica Peninsula, which is at a slightly lower latitude and has a warmer maritime climate. Some of the key components of the ice sheet are ice shelves and ice streams. Ice shelves are floating, and they play an important role in stopping the ice sheet falling into the sea. They act like flying buttresses on a cathedral. And ice streams are fast-flowing corridors of ice that move at over 800 meters a year. Examples of ice streams are the Pine Island and Thwaites glaciers, which you might have heard of because they are the glaciers that are losing the most mass in Antarctica today. Why is Antarctica important? This graph, which if you've been around for the last 2 weeks, you might have seen before, is from the recent IPCC report. The solid lines show sea level projections that assume only a small contribution from Antarctica. The dashed line shows a storyline where Antarctica's contribution is much greater. At present, 500 million people live within 2 meters of sea level, and so reducing the uncertainty around Antarctica's contribution to sea level rise is vital. But why are there unknowns? The map on the left shows the topography beneath the ice sheet. Nearly all of West Antarctica is below sea level. Parts of East Antarctica are also below sea level, such as the Wilkes and Aurora basins. Whereas ice that's on the side of a mountain will retreat up to cooler altitudes, where it will hopefully stabilize, ice that is grounded below sea level retreats down into a bath of meltwater and ocean water, which leads to even further melt. This process of rapid retreat is known as marine ice sheet instability. Some studies suggest that this process is already underway, and that the rate of retreat depends on our ability to reduce our greenhouse gas emissions. The map on the right shows Antarctica's ice shelves. Although ice shelves are floating and their breakup does not directly contribute to sea level rise, the buttressing effect that they have is really important. The passive areas of ice shelf in this diagram are shown in blue, and these segments can be lost without affecting the structural integrity of the ice shelf. But if these yellowy-brown areas are weakened, the ice shelf could rapidly disintegrate. If we go over 1.5 degrees of warming, we could lose all but the largest Antarctic ice shelves. Both of these processes are non-linear, and so they're very difficult to predict. And we've never seen an ice sheet collapse before, so as well as these known unknowns, there could also be unknown unknowns, which may come as a nasty surprise. Which brings us on to the last interglacial. This was the last warm period in the Earth's history. Global temperatures were 1 to 2 degrees warmer than pre-industrial, which is similar to the temperature increases we're experiencing now. This warming was caused by orbital forcing rather than increased greenhouse gas emissions. So it's not the same, but it can be used as a useful process analogue to give us an idea of future change. This graph shows last interglacial sea level reconstructions from coral high stands in the orange and Red Sea oxygen isotope data in the black. Although the best fit is a peak of around 6 meters, the data shows that sea levels could have been 18 meters higher or more. We know that 1.5 to 2 meters of this came from Greenland and almost half a meter from thermal expansion. This means that there must have been a significant contribution from Antarctica of at least 4 meters. However, previous modelling studies have been unable to simulate this. Ice sheet models are only able to generate less than 50 centimeters of melt from Antarctica, which doesn't correspond to the physical record. Some modelers have resorted to changing ice sheet model to simulate processes that are currently unobserved in Antarctica, such as Pollard and DeConte's cliff fracture mechanism. All of these previous studies use similar climate inputs, even though there is variation in CO2 concentrations between ice cores. So the question I asked was, what if CO2 levels were higher? Firstly, I ran some climate simulations. This slide shows peak CO2 from the ice core records in the left-hand table, and peak CO2 for my experiments is shown in the right-hand table. Sigma 0 is a standard last interglacial experiment from the Paleoclimate Model Intercomparison Project. Peak CO2 is 287.1 parts per million, which corresponds to the Vostok ice core data. However, peak CO2 in the various ice core records ranges from 282 to 298 parts per million. So I've increased peak CO2 by a standard deviation of 2, 4, 6, 8, and 10 to cover a range of 287 to 307 parts per million, which incorporates the upper values from the ice core records and then leaves some room for error. I'm not going to say too much about the climate model outputs because I'm here to talk about the ice, but I am in the process of writing a paper on the climate modelling part of my project, so keep an eye out for that. These are the surface air temperature anomalies. They show that as CO2 increases, air temperature increases around the coast, particularly around East Antarctica. Precipitation follows a similar pattern, with increased snowfall around the coast of East Antarctica. Ocean warming is concentrated around the Amory sector, which is here, and the Amundsen sector, which is here. I used the climate model outputs to force my ice sheet model, and I got the following results. The ice sheet model that I use has a basal melt function that simulates increased melt at the grounding line due to greater water pressure. Unlike the cliff fracture mechanism previously mentioned, this is an observed process. However, it is unknown whether or not this produces a more realistic simulation. So I ran the experiments with it switched on to generate a high melt scenario and then switched off to generate a low melt scenario. The solid lines on the chart are the low melt and the dashed lines are the high melt. So the Sigma 0 experiment only produces 16 to 130 centimeters of melt, which is nowhere near the 4 meters plus that the physical record suggests there was. In the high melt scenarios, a small increase in peak CO2 of only 4 parts per million is sufficient to generate over 4 meters of melt. In the low melt scenarios, a peak CO2 increase of only 16 parts per million is required to produce this much melt. So which parts of Antarctica lose mass? These maps show that the mass is largely lost from West Antarctica. By sigma 2, the West Antarctic ice sheet collapses, leaving a very large ice shelf, which probably isn't all that realistic, but never mind. 69% of melt just comes from just 4 catchments. There are 2 in the Ross Sea sector, and then the Pine Island and Thwaites catchments. The Pine Island Glacier and Thwaites catchments, as previously mentioned, are the areas of Antarctica that are losing the most mass at the moment. Small increases in mass are seen in parts of East Antarctica, but these are far too small to balance out the loss of West Antarctica. So there's only sort of 1 to 3 centimetres of increase there, compared to over a metre from certain sectors of West Antarctica. If we compare the simulated mass loss on the right with basal topography on the left, we can see that the areas of collapse closely correspond to the areas which were grounded below sea level. The Wilkes and Aurora basins remain intact despite being grounded below sea level. This could be due to cooler ocean temperatures in this area, an increase in precipitation, or a combination of these things. To find out whether atmospheric warming or ocean warming had a greater impact on mass loss, I ran experiments where only the atmospheric forcing was applied and experiments where only ocean forcing was applied. The dotted lines show the results for atmospheric-only forcing, and the dashed lines show the results for the ocean-only forcing. The ocean-only experiments follow the complete results, shown in the solid line, very closely, and so I found that ocean warming was key. So to conclude, slightly higher greenhouse gas concentrations in a last interglacial-like climate can generate the levels of mass loss suggested by the physical record. The margins are very small, with an increase of only 7 parts per million in CO2 equivalent required. This highlights the importance of tipping points in our climate system and the fragility of our largest ice sheets. So thank you for listening. We will now take a 10-minute break, and our next speaker will be Maxence.
Thank you so much, Helen, for this fantastic talk. Are there any questions in the room for Helen? Georg.
There are escape from those. Maybe I've got something wrong. Your simulations, they cover a range of CO2 concentrations somewhere considerably below the present day.
Yes.
First, why have you not also gone to 420, 450 or so? And have you, I mean, if I interpret this right, then on a longer term, West Antarctica is already determined to collapse. If you have it already with 380 parts per million or so. Or is there something I have not got correct?
Hang on, I shall go to the right slide. I tell you about the last interglacial. So I was telling you here about how...
No, I don't care about the degrees warming. You designed a range of
experiments, but this warming was caused by orbital. This warming was caused by orbital forcing, rather than increased greenhouse gas emissions.
Yeah, but then for your projections, do you use out of the ice core data a range of CO2 concentrations? And that goes from 282 to 300
yes, because
something.
This was what there was in the ice core record from the last interglacial.
That's okay.
So putting present day
and with some of
CO2
those, with a higher concentration, the sigma 8 or so, you derive already a collapse of Western Antarctica.
Yes.
Now we have already 412 or 15 parts per million.
The orbital forcing is different.
Okay, is it just that?
Yes. So it was much warmer then because the Earth was in a different
kind of force,
different bit of its orbit.
Okay.
So we could get higher temperatures with lower greenhouse gas concentrations. Pam.
Yeah, I guess I'm trying to understand this too. So you have calibrated your model against paleo records, but it's almost the same question as Georg, I guess, and maybe I didn't understand the answer. That were there not orbital forcing happening, then these CO2 concentrations would be enough to, over a long period of time, collapse the West Antarctic ice sheet. But if it's calibrated against the past, when did that occur? In other words, that's what I'm trying to figure out. Or how do you get these results based on the fact that in the past, when West Antarctica was lost, due to orbital forcing, we had these very minor fluctuations in CO2. Because I from Julie Brigham Greta's presentations, you see this, fluctuation between about 180 and 280. But I'm assuming those fluctuations were due also to the orbital forcing. And so you had CO2 fluctuating with that, but not necessarily causing the sea level rise that we saw in the past. So against what is it calibrating at a time in your past, or is it simply due to the CO2 forcing in the model itself? Is it I'm blanking on the proper term. Are you almost calibrating within the model as opposed to any behavior in Earth's past by the ice sheets? Is it internally consistent, or is it calibrated against something external to the model? If that makes sense. No. Okay.
I should have put my what the orbital forcing I used in here, but I didn't, because I thought it's only policymakers, and so they won't be that interested. So I put in orbital forcing set up for the last interglacial, and then because the ice core records have a whole sort of range of CO2, but the other modelling studies only use the Vostok value, I thought we'd use the whole sort of range and see what happens to Antarctica, to sort of explore small increases in greenhouse gas concentrations. Are there any other?
I'm still struggling, same as Pam probably. So is the message which we can take from your study into our situation, or even beyond in the future, basically that West Antarctica can collapse?
Yes.
But we cannot say we can compare our present day situation with one of the situations you have detected from the paleo records.
No, it's not exactly.
So it's kind of
comparable.
reduced to it can be.
Yes.
And it can be because of the mechanical and dynamical circumstances or these mechanisms.
Yeah.
Depending then whether it does or not, that depends on the time of the kind of forcing. So
I think probably
I
now
try
it would
to
be
get something out from for
probably
being
be
used today.
It would probably be worse now because we're warming both poles at the same time, and obviously the warming is much more rapid now than it was then. So you can look at this and think, well, Antarctica collapsed under this scenario, and the temperatures were similar to what we're experiencing now. So this sort of thing is likely to happen again.
And the probability is even higher since we have this
rapid warming. Yeah.
Okay. So a really urgent warning.
Come on, Thomas.
So briefly before coming to my question,
I can't hear you very well. Can you?
Sorry?
Can you move a bit closer to the microphone?
Yeah, I can. Thanks. So before coming to my question, if I understood it correctly, so on this question that was said before, I think it was also, if I understood it correctly, a sort of exercise to see if the physics in the model are complete, right? Because there is this discussion on whether ice cliff instability should be included in the models. But so what you found is that we don't need this mechanism in the model to already get the observed sea level rise.
Yeah,
Yeah.
sure.
But also now to my question. So these sigma 2, 4, 6, 8, and 10, are they like directly related to the uncertainty in the paleo CO2 record from the ice core? So is there, how precise is the ice core record on CO2?
There is an error bar around that, those figures there in the ice core record. So basically, the range that I've used is just the standard deviation, and so it just covers pretty much all the ice core record, because Dome C has the highest at 298, and that's kind of around sigma 4, sigma 6 in my experiments, and then it goes up a bit further than that. So, but we get the kind of sort of level of melt we would expect at sigma 4, so it's well within what's in the ice core record.
Thanks.
It's a follow-on from the other questions, really. How does the absorption from the sun's radiation into the ice change from the Earth being closer in your study to now, where we're further away, but there's, from the previous, we've got dust, we've got sort of bacteria, etc., and algae that are on the ice, which will increase the absorption of the solar radiation. So I'm not talking about the temperature, I'm talking about direct absorption of solar radiation, really. And how do the two compare?
Yeah, my climate models don't include ice sheets, which is one of the problems we have in modeling. And it's one of the reasons why climate models consistently underestimate warming at the poles. That's something we need to work on and have what we really need is a fully coupled climate ice sheet model, which is something that Maxence is working on in his PhD. We'll tell you a little bit about in a minute. So I think increasing the CO2 concentration does partially resolve this problem with underestimating warming at the poles, but it's still not quite perfect. We're still working on that. Does anyone else have a question? Okay, it is now time for a 10-minute break, and then Maxence will tell you all about his coupled climate ice sheet model experiments that he's about to start working on. Thank you very much.